thanks for anyone who's staying for this. So I'll be pretty quick. So I'm Ujjwal, I'm a PhD student at Berkeley. I'm going to give a quick talk on this new optimistic rollup that we're working on, and how we try to address security and decentralization issues in existing rollups today. So I'll briefly cover the motivation for this work, some background on EVM-based optimistic rollups that exist today, what the problems are with their approach, and what our solution looks like. And then briefly touch on some ongoing and future work. Okay, looks like my images aren't showing up, but that's fine. So we've heard this story countless times today. Ethereum doesn't scale. You can only do 10 to 15 transactions per second, and as a result, you have these high congestion fees when there is high demand. And so the question the community has been dealing with is how do you scale Ethereum throughput while maintaining decentralization? And so one potential solution here is validating bridges. And so how this works is basically you offload transaction execution to an untrusted executor. And off-chain execution state is periodically checkpointed with the validity guaranteed by either either a fraud proof or a validity proof. So I'll just talk about the latter. So in an optimistic rollup, you basically have a fraud proof mechanism that secures the state transition function. And so what you basically have is the L1 bridge contract accepts a validator state optimistically. And so other validators can submit these fraud proofs if they disagree with the state. And the L1 referee invalidates the assertion if it's incorrect. And so if the assertion is not invalidated within some time period, it's eventually confirmed. So the trust assumption here is that you have at least one honest validator. And okay, we can skip that. Oh, okay. So yeah, so basically this is a screenshot of what is it called? L2 fees, L2 beat, right? And it shows essentially the TVL on rollups today. And what you see here is that most of the liquidity, most of the TVL is in optimistic rollups, and most of that is in EVM-based optimistic rollups. And so it stands to reason that we should try to address the security and the security and decentralization issues of these systems. Even if we think that, okay, like ZK rollups are the future, it's still the case that people use these things today, and so we should be addressing these issues. So if you look at modern optimistic rollups, they try to optimize for a few things. They try to give you low-cost normal execution. They try to give you low-cost dispute resolution for when disputes occur. And they also try to give you an identical developer experience to L1, which means you have the same execution semantics at the instruction level, and you have minimal to no changes when you take your L1 contracts and redeploy them to L2. So yeah, you often hear of this referred to as EVM equivalent, whether these rollups are or aren't, but that's what they market themselves as. And so if you look at the common approach, it looks something like this. Basically, you take an Ethereum client like Geth, and you compile its implementation down to some lower-level virtual machine, and then you secure the rollup state with an interactive fraud proof on that lower-level virtual machine. So a challenger and a defender can narrow down a disagreement to a single step in the lower-level VM and execute that efficiently on-chain. Okay, this is going to be hard with no figures, but essentially, you have what this looks like more concretely is you have an Ethereum client like Geth. You adapt it to L2. You compile it down to a lower-level VM. And the resulting binary is committed to on L1 using some like vector commitment or polynomial commitment. And the IFP system enforces the execution of this binary at the target instruction level. So the key thing to note here is that the verifier is very strongly coupled with the client binary. And that has a number of issues, which, hard to illustrate here. But basically, because you're tying yourself to a binary, you can't introduce like other clients if you wanted to. So what this means is like if I have another client like Aragon or Besu, I can't use that to run the rollup. which means if there's a bug in get, then you're kind of screwed. Like that can bring down the network, that could cause invalid state transitions, and so it's not necessarily as secure as it can be. You're not able to leverage the decentralization of the L1. So for example, like Ethereum has several clients, and you can't leverage that decentralized trust. So you have to use this permission. Oh, there we go. Okay, finally. So this is what that looks like. You compile down, and then you Merkleize the binary. You put that on L1. So there's a problem of it being a permission system. And also, if you try to get around that, if you try to introduce several clients and use some K-majority scheme, that doesn't really address the issue either, because now validators have to run every single client. Okay, and so, right, so, and now as a user, you basically have to trust the correctness of the entire stack. You have to trust that the client implements the EVM correctly. You have to trust that the compiler compiles to this lower level representation correctly. And so this becomes like difficult to audit because there's tens of thousands to hundreds of thousands of lines of code. And it's also very infeasible to formally verify. So if you want to give formal guarantees, you can't really do that with this system. And yeah, and then the third problem is you basically, it becomes very difficult to throw away your upgrade keys, which is like something that all of these rollups want to do. Because if you change anything in the client system, that change has to be reflected on the L1 state commitment, which means everything has to go through L1 governance. And practically speaking, that means like someone has to have upgrade keys for the rollup. In practice, like Optimism has control over their contract, Arbitrum has control over their contract, and because of that, you have to trust them to not introduce some other change that you don't trust. So these are like the three main problems. Our solution, very simple. Basically, instead of doing the fraud proof at the lower level VM, you do it directly on the EVM semantics. So you construct one-step proofs for the EVM itself. And as a result, you get all of these nice properties. I'll be quick because there's no images here, so it might be boring. But basically, we address all three of these issues. And yeah, okay. So the system itself is pretty simple. We produce subproofs for each of these, each part of the EVM. So for the stack, for the memory, for the world state, we generate a proof, and we submit that during the one-step proof execution. And then the verifier just simulates the final state given some agreed upon initial state, agreed upon between the defender and challenger. And the current implementation, it's very simple. We only modify a few lines of code in get. We use standard interfaces, so we should be able to apply this to most clients, especially the ones that implement these interfaces. So Aragon does, Besu does, some others are planning to. And yeah, this is like basically what I've already said, so we don't have to cover it. We have some ongoing and future work. We are currently working on a client-agnostic bridge. We are currently also working on, well, a lot of these things are future work. If you're interested in them, come talk to me. We're also looking for people to help out on the engineering effort, so happy to chat about that. Oh, okay, it's backwards, that's why. Okay. And here's some links, and yeah, we're gonna have a new testnet live soon, probably within the next couple of days. So look out for that. You can follow our website, follow our Twitter, and yeah, that's about it. Thanks. Also happy to take questions if anyone has any. The what? Yeah. Yeah, so basically, so this is like comparing the types of rollups. So whether you're like quote unquote EVM compatible equivalent or what we describe as native. You can read the paper or blog post. We kind of talk about this in more detail. And then this is like specific rollups. So if you look at like Arbitrum and Optimism, Optimism initially was non-interactive. They've now since moved to an interactive proof mechanism. Both Arbitrum and Optimism compile down to some lower level representation. These two compile down to lower level representation, and then we target the EVM specifically, and so that's why we get some nice properties from that. Cool. All right. I guess that's it. Thanks.